Have you ever noticed how your phone can recognize a dog, a traffic light, a face, or even the texture of a leaf before you fully unlock the screen? Or how a self-driving car instantly interprets the chaos of the real world? Pedestrians crossing, bicycles approaching, signs half hidden by trees, and somehow makes sense of it all? Today, these abilities feel completely normal. They feel like magic we've grown used to. But what if I told you that just a little over a decade ago, computers were practically blind? They couldn't reliably tell a cat from a coffee mug in a photograph, couldn't decode the messy richness of real-world images, and struggled helplessly when the lighting changed or an object appeared from a new angle. And then suddenly, almost overnight, everything changed. A single scientific paper detonated across the world of artificial intelligence like a bomb, shattering the old way of doing things and announcing a new era. That paper was called ImageNet Classification with Deep Convolutional Neural Networks, though most people today know it by a much simpler name, AlexNet. And today, we're going to tell the story of how 3 researchers, 2 GPUs, and 1 giant leap in neural network design transformed computer vision forever. Before we dive into what might be the most influential paper in modern deep learning, make sure you like this video, subscribe to the channel, and hit that notification bell so you never miss a deep dive into the breakthroughs that built today's AI. All right, let's enter 2012, when the world of computer vision was about to change forever. Back then, the story of image recognition was a story of limitation. Researchers relied on handcrafted features, painstakingly designed mathematical tricks intended to capture edges, corners, gradients, and other low-level patterns in an image. Algorithms like SIFT and HOG dominated the field, and on small benchmarks like MNIST or CFAR, they performed reasonably well. But the real world is not tidy. Objects can appear in countless conditions: dark or bright, rotated, partially occluded, blurry, messy, colorful, or half-cropped. No matter how carefully engineers wrote their feature detectors, they were still trying to compress the infinite diversity of the visual world into rigid, manually designed formulas. And that meant performance could only go so far. But at the same time, something extraordinary was happening. A new dataset had arrived: ImageNet. Imagine 15 million high-resolution images spanning more than 22,000 categories. Everything from breeds of dogs, to species of insects, to kinds of furniture, to tools, foods, plants, landscapes, an enormous visual dictionary of the world. And at the center of this dataset was a competition. Classify images into 1,000 specific categories using a training set of 1.2 million images. This challenge, ILSVRC, was brutal. Models were scored not just on whether their top prediction was correct, but on whether the correct label appeared in their top 5 guesses. Before 2012, the best systems had top 5 error rates around 25%. People believed this task was simply nearing the limits of what algorithms, especially deep learning, could do. Enter Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton. Their idea was simple but daring: build a massive deep convolutional neural network, feed it raw pixel values, and let it learn every useful feature on its own. No hand-engineered edges, no clever human priors, just pure learning. But there was a catch. A network big enough to solve this problem would have tens of millions of parameters. Training it would require enormous compute at a time when normal CPUs simply couldn't handle it. The breakthrough was the GPU, specifically the NVIDIA GTX 580 with its then gigantic 3 GB of memory. Not enough for the full model, but enough if you got creative. So the team did something bold. They split the neural network across 2 GPUs. This was not trivial. They needed the GPUs to communicate only at key layers to avoid massive computational slowdown. But by dividing the filters and feature maps across GPUs, carefully restricting which parts of the network talked to which, they built a model that simply couldn't have existed otherwise. And what a model it was! AlexNet consisted of 5 convolutional layers, followed by 3 fully connected layers for a total of 8 learned layers and about 60 million parameters. From the perspective of an image entering the network, the journey begins with a 224 by 224 pixel crop of the original downsampled image. The first layer applies 96 filters sized 11 by 11, stepping across the image with a stride of 4 pixels, detecting basic patterns like edges, color gradients, and orientation. The next layer uses 256 filters of size 5 by 5, building more complex structures from the ones below. Then come 3 convolutional layers with filter sizes of 3 by 3, having 384, 384, and 256 filters respectively. These deeper layers learn features like object parts, curves, textures, fur, eyes, wheels, stripes, patterns that become meaningful only when built on multiple levels of abstraction. After that, the spatial information is flattened and fed into 3 massive, fully connected layers with 4,096 neurons each, culminating in a final 1,000-way softmax classifier that outputs probabilities for all image categories. But architecture alone wasn't the reason AlexNet crushed the competition. One of its most revolutionary ideas was something incredibly simple: replace saturating activation functions like tanh with the rectified linear unit, or ReLU. Instead of squeezing every input into a limited range, ReLU simply pass positive values through unchanged and output 0 for negative ones. This small change accelerated training dramatically. In fact, experiments on smaller datasets had shown ReLU networks learning several times faster than those using traditional activations. Without ReLUs, training AlexNet on 1.2 million images would have been nearly impossible within a practical timeframe. Another innovation was local response normalization, inspired loosely by biological neurons. In essence, it encouraged neurons detecting similar spatial patterns to compete. At each location in a feature map, a neuron's activation would be divided by an expression involving the squared activations of neighboring channels. This promoted sparsity and robustness, boosting generalization and reducing error rates by more than 1%. And then there was overlapping pooling. Instead of pooling over non-overlapping regions, AlexNet used 3 by 3 pooling windows with stride 2, meaning the windows overlapped. This seemingly small design change helped the network capture smoother transitions and slightly reduced overfitting. But perhaps nothing was more important than the techniques to prevent the network from memorizing the training data. With 60 million parameters and just over 1 million images, AlexNet was at constant risk of overfitting. The solution began with data augmentation. The simplest form involved taking random 224 by 224 crops from 256 by 256 images, along with their horizontal flips. This alone expanded the dataset by a factor of over 2,000 and forced the model to become invariant to shifts, translations, and reflections. At test time, instead of using a single crop, the model evaluated 10, 4 corners, the center, and their mirrored versions, then averaged the predictions. A second augmentation involved altering image brightness and color using PCA. By computing the principal components of RGB pixel intensities across the dataset, the model simulated natural lighting changes, like slightly warmer sunlight or cooler indoor light, by nudging each image along these principal color directions. This helped the network become insensitive to illumination changes, shaving off more than a full percentage point of error. But the true regularization superstar was dropout. In the fully connected layers, the model randomly set half of all neurons to 0 on each training pass. This meant that every input effectively passed through a different thinned network, forcing neurons to learn features that were useful in multiple combinations, rather than co-adapting too tightly. Dropout nearly doubled the number of training iterations needed, but without it, AlexNet would have overfit catastrophically. Training AlexNet was itself a marathon. Using stochastic gradient descent with a batch size of 128, momentum of 0.9, and weight decay of 0.0005, the team trained for about 90 epochs, roughly 5 to 6 days of non-stop computation on 2 GPUs. Weights were initialized from a small Gaussian distribution, and biases in certain layers were set deliberately to 1 to ensure ReLUs received positive inputs early on. The learning rate started at 0.01 and dropped by a factor of 10 whenever progress plateaued. Week by week, epoch by epoch, the model learned to recognize the massive, messy world of ImageNet. And the results? Absolutely shocking. On the ILS-VRC 2010 dataset, AlexNet achieved a top 1 error of 37.5%, and a top 5 error of just 17%, crushing the previous records by huge margins. Competitors hovered in the mid-40s for top 1 and mid-20s for top 5. AlexNet blew past them with improvements of 8 to 10 percentage points. In the 2012 competition, a version of the model achieved 15.3% top 5 error when averaged across multiple networks, the winning entry by a massive gap. Nothing else even came close. This wasn't just better performance, it was a paradigm shift. It was proof that deep convolutional neural networks, trained on GPUs with clever regularization and high-capacity architectures, were the future of computer vision. Even qualitatively, the network showed remarkable intelligence. The filters learned in the first layer, shown in the paper's visualizations, look like edge detectors, color patterns, and texture primitives. Higher layers activated strongly for semantically meaningful parts of images. The model could retrieve visually similar images based not on pixel-level similarity, but on high-level abstract features, demonstrating that it had learned something approaching human-like representations. The aftermath of AlexNet is the world we live in now. Every breakthrough in vision, VGG, GoogleNet, ResNet, EfficientNet, traces its lineage back to this moment. Every application that relies on automatically understanding images draws from the deep learning revolution that began with this paper. AlexNet didn't just win a competition. It proved that learning features automatically from data was not only possible, but superior to manually engineering them. It showed that bigger datasets, bigger models, faster hardware, and smarter training techniques could unlock levels of perception previously thought unreachable. It declared the beginning of modern AI. So next time your phone recognizes your face, or your car detects a pedestrian, or an app instantly sorts your photos into categories you didn't even know you had, remember, these abilities exist because 3 researchers dared to build a network too big for the hardware of its time and trained it until it could see. This is the legacy of AlexNet. Thank you for watching this deep dive into one of the most important AI papers ever written. If you enjoyed this video, don't forget to like, subscribe, and comment below with the next paper you want us to explore. Your suggestions drive this series, and the best ones will absolutely become future episodes. See you next time for another journey into the breakthroughs that built today's AI.